Welcome to the Explainer. You know how everything in our world seems to be connected, especially when things are moving? Well, today we're going to dive into a calculus concept called related rates. It's this amazing tool that lets us see the invisible threads connecting different speeds and changes all around us. So, to get started, let's set the scene with a classic puzzle. Just picture this, a 15-foot ladder leaning against a wall. We'll call the distance from the wall to the ladder's base x, and the height it reaches up the wall y. For now, everything is perfectly still. But now, here's where it gets interesting. Let's introduce some motion. What if we start pushing the bottom of that ladder towards the wall at a nice, steady pace? Let's say 1/4 of a foot per second. Now, you might think the top would just slide up at the same speed, right? But nope, it doesn't. So how fast is it moving, and does that speed stay the same? That's the mystery we are going to crack today. To solve this, our first clue doesn't actually come from the movement itself. Weird, right? It comes from a simple, timeless geometric rule that kinda locks the ladder, the wall, and the ground together in a single snapshot of time. And that rule is, you guessed it, the good old Pythagorean theorem. At any given moment, x squared plus y squared has to equal 15 squared. This gives us a perfect snapshot of the ladder's position. But here's the thing. A snapshot isn't enough, because our ladder is in motion. So here's the big question. How do we take this equation, which is basically frozen in time, and make it come alive? How do we get the idea of speed and motion into a static geometry formula? Well, in calculus, we have a magic key for this. It's called the derivative with respect to time, and we write it as d/dt. When we apply this little operator to a variable, it tells us exactly how fast that variable is changing at any given instant. So dx/dt is the speed of the ladder's bottom, and dy/dt is the speed of the ladder's top. So watch this. When we use our d/dt key on our static rule, using a technique called implicit differentiation, which is really just a way of looking at how each part changes over time, the whole thing just transforms. It unlocks a brand new relationship, one that connects not just the positions x and y, but their speeds, dx/dt and dy/dt. This is that hidden connection we've been hunting for. What's so cool about this is that we can turn this whole process into a simple, repeatable, 4-step strategy. And it works for any related rates problem you'll ever see. It's like a universal blueprint for solving these kinds of motion puzzles. So here it is, the master plan, just 4 simple steps. First, you sketch it out, draw what's happening, and label everything you know and what you're trying to find. Second, you find that static equation, that geometric link, just like we did with Pythagoras. Third, and this is the magic step, you differentiate with respect to time to bring the motion into the picture. And finally, you just plug in your numbers and solve for whatever's missing. Easy. All right, let's put this plan into action with our ladder. First, what do we know? We know the speed of the bottom, dx/dt, is -1/4 feet per second. And notice it's negative. Why? Well, because that distance x is shrinking, it's decreasing. We want to find the speed of the top at the exact moment when x is 7 feet. A quick little calculation using our original Pythagorean theorem tells us that at that instant, y has to be the square root of 176. The only thing left to find is dy/dt, the speed of the top. And now for step 4, we just plug everything we know into our new unlocked equation. We substitute 7 for x, -1/4 for dx/dt, and the square root of 176 for y. Then after a little bit of algebra, we just isolate dy/dt, and boom, there it is. We've solved the mystery. At that exact moment, the top of the ladder is moving upwards at 7 divided by 4 times the square root of 176 feet per second. It's a very specific number, which proves what we suspected at the start. The speed isn't constant. It totally changes depending on the ladder's position. And this right here is what makes this whole thing so powerful. The scenario can change completely. Maybe it's 2 people walking apart, where the distance formula is your static equation. The picture looks different, the first equation is different, but that 4-step process for finding the hidden speeds, it's exactly the same. Okay, so that was a fun puzzle, but is this just some neat math trick, or does it actually matter out there, in the real world? Oh, it absolutely matters. It matters because the world is just filled with things that change together. Think about an oil spill expanding in the ocean. The rate its area is growing is related to its radius. Or a rocket blasting off. Its changing altitude is directly related to its velocity. You even see it in economics, where the rate of inflation is related to the rate of unemployment.
Related rates is the tool we use to model all these complex, moving systems. So, the next time you see something in motion, just think about the hidden connections that are at play. From the changing angle of the sun and the growing length of a shadow to the rate your phone's battery is draining versus how far you are from home. Understanding related rates gives us the tools to describe, predict, and even engineer this beautiful, dynamic world all around us.